Hello and welcome back to another video, everybody. Today I'm going to be going over a technique of integration. I'm going to go over the disk and the washer method. Now, what are those methods and what are they used for? Let's get into it. Let's say you have a function that kind of looks like this, all right? This sort of quarter circle formed by this line. Now, we can find the area of this as long as we know what the function that describes it is by using integration. But let's throw in something tricky here. What if we rotated this around the x-axis to create a three-dimensional solid object? Whoa, I mean, come on, that sounds like three-dimensional stuff. Isn't that like calculus 3? I mean, why are we talking about it right now? Well, when it's something like this, we can use what's called the disk method to actually find what the volume of that solid would be. To do this, we're going to extend how we define integrals. Now, we already know that integrals are taken with respect to dx or d, whatever the variable is, because it's an infinitely small slice of whatever the x-axis is. Now, the way that helps us in a normal integral would be that we are able to create an infinitely small rectangle, which represents an infinitely small chunk of the area. And when you add the infinite rectangles present in the area that we're trying to find, you get the total area of the part under the function, right? That's what integration is. Now, what if instead of infinitely small rectangles, we had infinitely thin disks? Now, what I mean by that is that instead of having the integral of, point A to point B, whatever that is, of some function of x with respect to x, this dx, this shows f of x is the height of the function times an infinitely small slice. It's literally a rectangle, right? That's the area of a rectangle, one side times the other. What if instead we somehow got the area, or I guess volume, of an infinitely small disk? Well, a disk is a circle, so what's the area of a circle? That's pi r squared. What's the radius? Well, if we rotate this around the x-axis, the radius is going to be whatever the height is at that point, which means that our radius is actually still going to be f of x, but it's pi r squared, so our radius, f of x, is going to be squared. Let me write this a little better. And then we still have the pi. Now, pi is just a constant, and so we can take it outside of the integral and multiply it in later. So this is our expression. Instead of finding the area by integrating with f of x and dx, now we have the integral of the volume with pi r squared, r being f of x, times dx, right? Because we're still multiplying by dx, because it's essentially, a disk is a cylinder with a height of 0, right? Or at least, in this case, the limit as it approaches 0, because dx is an infinitely small, approaching 0 slice. So how do we evaluate that for a function like this? Well, a half circle is, we'll say this point is 1, and this point is also 1, right? 1 on the x, 1 on the y. That gives us a function of x squared plus y squared is equal to 1. All right, well, let's get this into just terms of y. Y squared equals 1 minus x squared, and so y is equal to the square root of 1 minus x squared. So that's our f of x. Y is f of x, remember. So now, to find the area of the solid, let's plug it into this. As you can see by the graph, we're going to be integrating from 0 to 1, and our function of x is going to be the square root of 1 minus x squared. And based on this formula right here, we'll be squaring that and then having pi in the front. Now, the first thing that we can do, very obviously, is cancel this square with this square root. And that gives us a much, much easier integral to deal with. So let's solve this. Doing that, we're going to see that we just have to apply the reverse power rule to each of these terms. 1 becomes x squared becomes 1/3 x cubed, because both of these cases, you're adding 1 to the power, and then you are just bringing it to the front to divide. All right, so evaluating this expression, we'll have pi times Okay, well, we don't have to worry about when it's evaluated at 0 because these terms are both 0, so that'll cancel out. So we can just evaluate it at 1. Evaluating it at 1, we'll get 1 minus 1/3 times 1 cubed. 1 cubed is 1, so it's all just 1/3. 1 minus 1/3. That's 2/3, and we still have a pi. So this is going to be 2/3 pi. All right, great. Now, that was a specific case of the disk method, right? We used it for a function that we know. But the methods that I just used are actually used in proving the formula for the volume of a sphere. If you noticed, since we had a half or a quarter circle as our function, when we rotated it, we actually got half a sphere. So if we were to multiply the area that we just got by 2, we would get the whole sphere, and we'd have 4/3 pi. Now, we can use the disk method again to do this for any radius. So let's do that real quick just to show you. The only thing we have to change is the 0 to 1 becomes 0 to r. And since we had x squared plus y squared is equal to 1 before, we're actually going to get x squared plus y squared equals r squared. That's the general formula for a circle. And so when you work that out, you'll get y is equal to the square root of r squared minus x squared. Do the same thing when you have the square root and then you're squaring the f of x. You'll get this expression. Okay, so now we just apply the reverse power rule. We'll get r squared x minus 1/3 x to the third power, evaluated from 0 to r. Don't have to worry about it evaluated at 0. Plugging in r here and here, we'll get r squared times r, that's of course r cubed, minus 1/3 r cubed is going to leave us with 2/3 r cubed. So our final expression is 2/3 pi r cubed. But remember, since we rotated a quarter circle around, that means we only got a half sphere. So doubling it, we get that the general formula for the volume of a sphere based off of its radius is 4/3 pi r cubed. And you can look that up and verify. You can test it with various values and verify. But yeah, that's correct. That's the formula for the volume of a sphere, and you can derive it fairly simply using the disk method of integration. In the next video, we'll discuss the washer method, which is basically just the disk method, but twice. It's not too difficult to explain since you already know the disk method now, hopefully. So next video will probably be a shorter one. But hopefully you're able to understand the disk method now. You'll be able to see another example in the washer method video coming up soon. But for now, thank you guys so much for watching.